How about the proof of the Orbit-Stabilizer Theorem? The key initial observation to trying to think about the proof of the Orbit-Stabilizer Theorem is to realize this equation is equivalent to the following equation. Take the order of G, leave some space here. Take the order of G, divide by the order of the stabilizer of I and G, and that's going to be equal to the number of elements in the orbit. And I purposely left some space there. By Lagrange's theorem, what did Lagrange's theorem say? It really says two things. It says you got a finite group G and a subgroup H. The order of H has to divide the order of G. It also says the index of H and G equals the ratio here where this H is supposed to be the stabilizer. It equals the order of G divided by the order of the subgroup. This is the key. I mean, you could conjecture the orbit stabilizer is true from examples. You're trying to prove it. This is the key observation to realize this equation is equivalent to this equation. In other words, the index, we want to really prove the index of H and G is the same as the number of elements in the orbit. They have the same number of elements. What does the index mean? I could put this definition on the next test. The index of H and G is the number of left cosets of H and G. Again, in this case, H is the stabilizer. How does this observation help? It motivates the idea of the proof. The idea of the proof is to come up with a one-to-one and onto function from the collection of left cosets of the stabilizer in G to the set that is the orbit of the given I. The idea of the proof, is to come up with a one-to-one and onto function which in real analysis, you're going to almost always call a bijection. A bijection. If you got a function that's one-to-one and onto, that's most commonly called a bijection, to use one word. There are actually also other names for one-to-one and onto. One-to-one is also called an injection. A one-to-one function is called an injection, and an onto function is also called a surjection. Kind of fun, fancy names. If it's both one-to-one and onto, it's called a bijection, or a one-to-one correspondence. You can match up these sets. Come up with a one-to-one and onto function, a bijection, between the collection of left cosets of H and G, where H is the stabilizer of I in G, to what? The orbit. Notice I put curly braces around these words here to emphasize it's a set. It's the collection, the set of all possible left cosets. Actually, this set does have a specific symbol. We'll see in chapter 9, which you should actually start reading today or tomorrow, that this is also written like this. Almost as if you're writing a fraction here. This is called the, in our book specifically, it's called the factor group of G by the stabilizer of G, of I and G. Other books call it the quotient group. I will go ahead and write factor group like our book does. Factor group of the stabilizer in G. Is it a fraction? Not technically speaking, but it kind of acts like a collection of fractions in a sense, but I don't want to go into details at the moment. But how do you come up with such a one-to-one and onto function? You got to think of something, don't you? In this very abstract situation, we don't know what G is, we don't know what S is, we don't know what I is. We do know G is a group of permutations on S, and the I is an element of S. And the stabilizer is all the things in G that map I to itself. Well, I come up with a transformation here. In fact, the book does call this T. Here's our bright idea, if you will. Bright idea. Define a transformation T. In fact, I'll call this T here like this. T has got to map a left coset of the stabilizer to something in the orbit of I. What does a left coset look like? It's something in G times, so to speak, the stabilizer, the H, right? Usually we write left cosets like this. What does that look like in this set here? The A is a permutation in G. I think the book calls it phi, but I'm going to call it alpha, because we've usually called permutations alpha. And what's the H? The H is the stabilizer. Maybe you want to make it a bit bigger than usual, or maybe you want extra parentheses in here or something. That's a left coset, arbitrary left coset. The alpha is in G. What do I map it to? In the orbit of I with respect to G. What does it mean to be in the orbit? It means there's some permutation that maps to that element that's in the orbit. How can I take what I've got here, this left coset, and come up with a symbol, an expression that I know for sure is in the orbit of I? The only thing that I can possibly think of doing is to write alpha of I. Right? That's the only way I can use the symbols that I've got here, where alpha is in G, this group of permutations on the set I, and I is an element of S, the elements that are being permuted. By definition of the orbit, that's going to be an element of the orbit. For sure, this is an element of the orbit. That's our bright idea, is this is going to be our function that we hope is one-to-one and onto. And if it is one-to-one and onto, then this has got to be true. They've got to have the same number of elements. And if G is a finite group, so you can apply Lagrange's theorem, we are assuming G is a finite group, I can say these are equal, and therefore I can say this is true. So what's there to do? You do need to show T is one-to-one and onto, but you need to do something else first. And I think this is going to be the only thing I do today. And maybe you should read the rest. This is a very important point. Going to come up in chapter 9 as well. You need to verify T is something called well-defined. What does that mean? It means basically that it makes sense. Does this formula make sense? It kind of looks like it should make sense. I mean, I wrote it down. Why shouldn't it make sense? Here's the trick. Left cosets, the representative in front of the left coset, like the A here, are not unique. The representative. A could equal B. Okay, AH could equal BH, even if A and B are different. That can happen, right? It would be equivalent to saying A inverse B is an H, which is also equivalent to saying B inverse A is an H. But that doesn't mean A equals B. I'm taking this arbitrary left coset with the alpha as the representative, like the A or the B here, and I'm mapping it to something involving alpha. But what if I used a different representative, call it beta, for the same left coset? How would I know I get the same thing in the orbit? How would I know if I use the beta, where it's the same left coset, that beta of I would be the same as alpha of I. That's what you got to prove. It's a very important point. Is T well defined? Does it make sense? Does its formula make sense? i.e., if alpha times the stabilizer, that left coset equals beta times the stabilizer, this left coset, where alpha and beta could be different, does alpha of I equal beta of I? That's the big question. It better, if this is going to be well defined. So how do you do this? How do you prove this? This is true. The answer to this question is yes. But why? The answer is yes. But why? Okay, well, let's assume the left cosets are the same. What does that mean? Assume this is true. Well, just like on the previous page, it means these kinds of things are true right there. That big lemma about coset properties. I can imply that here. Instead of with A, B, and H, it's with alpha, beta, and stabilizer. This means, for example, that alpha inverse beta is an element of the stabilizer. It also means beta inverse alpha is an element of the stabilizer. But what does that mean? What does it mean to be in the stabilizer? It means this function, alpha inverse beta, maps I to itself. But by definition, alpha inverse composed beta of I is alpha inverse of beta of I. Now apply alpha to both sides. Plug both sides into alpha. I hope that was clear. You're trying to get rid of the alpha inverse here. And yes, alpha and alpha inverse are inverses. If I want to really emphasize that, I could write alpha, alpha inverse in parentheses like this. I could replace that with an epsilon if I want, where epsilon is the identity. And then epsilon of anything is the anything. Beta of I equals alpha of I. Okay, I showed more steps than I probably really need to there. But that's the idea.
How do you drop the stabilizer there? How do you get rid of the stabilizer on the right side?
Over here, you mean?
Yeah.
I'm using the definition of what it means to be in the stabilizer. This compositions in the stabilizer means that it maps I to itself. That's what the stabilizer of I is. It's all the permutations that map I to itself. So I'm thinking about an abstract ideas here rather than the particular example. Be in the stabilizer of I means you map I to itself.
And that's just a property of.
That's just what the stabilizer is. It's its definition. This is a property of, this right here is a property of cosets. Properties of cosets, I did emphasize, if not Monday, before spring break, are really, really important. They're important in chapter 7. They're important for the rest of the course, really. Cosets show up the rest of the course, not just in group theory, but also in ring theory. We start chapter 12 after Easter. You want to make sure you know the properties of cosets. So that's a proof, basically, that this function T is well defined. You'd also have to show it's one-to-one and onto. Actually, the proof that it's one-to-one is basically the reverse argument of all these things. All these things are reversible. Assume alpha of I equals beta of I. In other words, assume you got the same outputs here for this formula of T. Show the inputs are the same. Show the left coset is the same. All these steps are reversible. And you'd ultimately allow you to say this is true. That would be enough to show T is one-to-one. What's the idea of why it's onto? Give me something in the orbit of I. What gets mapped to it under T? to be in the orbit of I means there's some permutation that maps I to that given element. You could call it J. Call that permutation alpha, then by definition, T of this would be alpha of I, which is J. Catch what I just said there? Went by fast. Give me something arbitrary in here, call it J. What does it mean for J to be in the orbit of I? It means there's some permutation, call it alpha, such that alpha of I equals J. For that alpha, this would map to J. So it would be based on the meaning of the orbit.